This video is going to be an introductory video for section 5.4, but before we get into the notes, I'd like you to do a little warm-up. There are two problems here. One is a graph, one is a data table. So for number one, pause the video here and then come back to the video to get to number two. Pause the video and then you can come back for the answers. So for number one, a particle's velocity in feet per second is illustrated in the graph at the right. Approximately how far did the particle travel in the first 3 seconds? For number two, the table at the right gives the data for the velocity of a vintage sports car accelerating from 0 to 142 miles per hour in 36 seconds, or 10 thousandths of an hour. Approximately how far did the car travel during the 36 seconds? So for number one, if you needed to partner up to try and remember how you figure out the distance a particle traveled when you're given the graph of the velocity, you have to remember that you could have either counted the squares under the curve or you could have used trapezoids. So if you remember, the y values are in feet per second and my x values are in seconds. When I multiply those together, I'm just left with feet, which is the distance traveled. So I used a trapezoid. I used 3 trapezoids going from 0 to 3. My width was 1, so I factored that out, and then I took 1/2 times the first y value plus the second and third y values plus 1/2 times the fourth, and I got 9.5 feet. If you had counted squares, your estimate should have been somewhere around there as well. For number two, when you're given a data table, you first of all want to make sure your time and velocity is in the same units. And I converted the hours, or the 36 seconds, to hours for you. My delta x is the same each time. It's always 0.001. So I factored that out, and then I multiplied it to all my y values, with my first being multiplied by 1/2 and my last being multiplied by 1/2. And the car traveled 0.97 miles in 36 seconds, so almost a full mile, or in feet, that's 5,121.6 feet. So the reason I had you guys do this as a warm-up was because we are getting back into discussing and looking at area under the curve. And so what I want you to do is pause the video, and I want you to take some time to work on the Riemann sum exploration, section 5.4, and go over it or look at the answers when you're all done. And then when everyone is done, come back to this video, and what you don't finish today, we will finish on Monday. So section 5.4 covers definite integrals and Riemann sums. And so definite integrals we touched on very briefly in chapter 1, talking about counting the squares and trapezoids, so figuring out the area under the curve. We're going to learn another way to estimate the area under the curve. But just a reminder, a definite integral is a way to find the exact area under the curve. And so we've been using tools to approximate that area. But what we're going to be getting into is, if you recognize this integral notation at the bottom, lately you guys have been finding antiderivatives when you're given an integral of f of x dx, but you haven't had what we call limits of integration. You haven't had an a there and a b there. You've been finding a general equation of an antiderivative, and but when you put limits of integration there, when you do the antiderivative and you evaluate it from a to b, you are going to get a specific value. So the next way that we're going to approximate the area under the curve is using a different shape, and this time we're going to be using rectangles. And so there are a couple different ways that you can use rectangles. There's a left Riemann sum, a right Riemann sum, or a middle. And so I'm going to show you guys some notation and then show you how to calculate or approximate area under the curve using different Riemann sums. So a couple things about notation first. Some of this is going to be familiar from trapezoids. N is going to be the number of rectangles. So if we say to use a Riemann sum where n equals 4, that would be 4 rectangles. If we said to use a trapezoid rule where n was 3, we'd use 3 trapezoids. So that's the same. N represents the same number of shapes that you're going to be using to approximate the region, the area. X sub 0, x sub 1, x sub 2, these are our endpoints, meaning the left and the right of each rectangle that we're going to use. Delta x is the same that we used for trapezoids. Delta x should be the same if you're using an equation or a graph. These might be different if you're using a table. And then C sub 1, C sub 2, C sub 3, etc. These are our sample points. And these are the x values for which we're going to use the y values for to determine the height of each rectangle. So let's first start out with what we call a left Riemann sum. So you'll see that we have the L with a little sub 4. That means to use a left Riemann sum. So if I'm going from A to B, what I'm going to do is from A to B, it's already a width of 4. So I'm going to, each width of my rectangle is going to be 1. And then my sample points, I'm going to start on the left side of each rectangle, so C1, C2, C3, and C4. I'm not going to use the far right one because that's the right side of the rectangle. We only want to use the left side. And then the height of each rectangle goes to the y values at C1, C2, C3, and C4. And so then we find the height and multiply it by the width, and so that's the area of the rectangle. We add all 4 together, and that approximates the area under the curve. And as you can see, there is some area that we are leaving out. And so there will be times where you're asked to use a Riemann sum, and then is it an overestimation or an underestimation? And it varies. A left Riemann sum is not always an under. It depends on if the function is increasing or decreasing. So let's compare that to a right Riemann sum. So a right Riemann sum is denoted with an R sub 4. So notice I'm still using A to B. I'm still using the same endpoints. Nothing has changed there. Excuse me, except my sample points now have shifted to the right side of each rectangle. And so now I've drawn my rectangles up to the height of where the y value is at C1, at C2, so where it is on the curve or the function that we're given. And now you'll notice that I'm including some area that's above the curve. And so for this particular example, my right Riemann sum is an overestimation of the area from A to B. And then another Riemann sum that we're going to be using is called a midpoint Riemann sum. So once again, I'm still going from A to B. My endpoints of my rectangles didn't change, but now my sample points have shifted to the middle of each rectangle, and hence the name midpoint, and that will be denoted with an M sub 4. And so my sample points go from between x sub 0 and x sub 1. It's going to be halfway between, and so my rectangle is the height at C sub 1. And then my second rectangle is at the height of C sub 2, so the midpoint. And you'll notice that sometimes I have my rectangle is outside above the area, above the curve, and sometimes I'm leaving out the area. So in this case, a midpoint is a little bit more of a better estimation than my left or my right. But that midpoint isn't always going to be in the middle of a left and a right, because if a function goes up and down, increases and decreases, it can vary your estimation. But no matter what type of Riemann sum you are using, you are going to use the same type of formula. And it's just the sum of a bunch of rectangle areas, so the height times the width. And so in this case, I would have my height of my rectangle times my width of my first rectangle, and then plus the height of my second rectangle times the width of my second rectangle, etc., until however many rectangles you're using. If your delta x is the same, of course you can factor it out and then just add all the heights together, or the y values at all your different sample points. So I'm going to talk a little bit more about notation with this, and then we'll get into some example problems. So before we get into some notation, I want to see how many of you guys recognize sigma notation. Sigma is a Greek letter. It's used a lot in probability and statistics, and it means the sum of many parts. And so in this example, this is telling us to go from 2 to 5. We're going to plug 2 through 5 in for k, and we're going to add all the values together. And so that just means 2 plus 3 plus 4 plus 5, and we get 14. If this had been k squared, I would add 2 squared plus 3 squared plus 4 squared plus 5 squared to get my value. And so what this has to do with Riemann sums is it's getting into our notation. So as I said before, the area is just your height of your rectangle times your width, and you add them to all the different rectangles. We can convert this into sigma notation. And so when I change it into sigma notation, I'm going from 1 to n, so as many rectangles as we have. Here's my height of each rectangle times my width of each rectangle. And that's just kind of the shortened version of telling me to add up all of the rectangle areas. But with calculus, you want more and more rectangles. So if we add the limit notation in front as n goes to infinity, that means the more rectangles you have, the more accurate your answer is to the actual area. And so we added this limit notation, and what that does is convert our sigma notation into an integrand. And so that's how a definite integral is related to a Riemann sum. So a Riemann sum is the approximate, but as soon as we add that limit notation in front of our sigma notation, it creates a definite integral in which you're going to get the exact area. So let's walk through a couple of examples of how you could calculate the area under the curve. So this first one, I'm not giving you the equation of the graph. I just want you to estimate the area under the curve below from 1 to 4 using 3 rectangles using left Riemann sums. And so that means that I am going to draw my rectangles. So going from 1 to 4, my width is going to be 1, and my height is going to be first at 1, my second rectangle's height is going to be at 2, and my third rectangle's height is going to be at 3. And so when I have a width of 1, I can factor that out, and then I just estimated the height at each of my points where my rectangles hit that curve. I estimated it to be about 1.3, 2.3, and 3.7. When I add those together, I get 7.3. I'm going to do the same thing, but with a middle Riemann sum. So now what's going to change? My endpoints are still 1 to 4, my width is still 1, but now I'm going to go to the midpoint. So between 1 and 2 is 1.5. That's the y value that I'm going to use at 1.5. Between 2 and 3, I have 2.5, so my rectangle is going to go up to where 2.5 hits the graph, and then from 3 to 4, at 3.5 is my midpoint, so my rectangle will be at the y value of 3.5. So when I estimate these y values, I got 1.7, 2.8, and 4.6. When I add those together, I get 9.1. And lastly, we have a right Riemann sum. So still going from 1 to 4, still using 3 rectangles. Now my right side is going to be 2, 3, and 4. So draw a rectangle, for the right side of going from 1 to 2. It will show up. Maybe not. Let's see if this other one does. There we go. So I went from 2 to 3. Here's where it hits the curve at 3. From 3 to 4, this is where it hits the curve at 4. And my other one doesn't, oh, there it goes. And from 1 to 2, my right side. And then I estimated my y values to be at 2.2, 3.6, and 5.9, and I got 11.7. And so because this was an increasing function, you'll notice that my estimates from left, middle, and right, it went from 7.3 to 9.1 to 11.7. And this would be an overestimate of the area under the curve. And so then I was going to show you guys, yes, there is a way to calculate Riemann sums using a program on your calculator. So remind me when I get back to give you this program. And so we can use the program when you know the equation of the function and then your lower and upper limit and then how many rectangles you want to use. So remind me when you see me to give this program to each and every one of your calculators. Okay, so what happens when you don't have the graph and you're given a table of values? So this one says you're walking along the bank of a tidal river watching the incoming tide carry a bottle upstream. You record the velocity of the flow every 5 minutes for an hour. So you can pause the video and see if you guys can come up with this on your own. And then I will be going over the answers. So notice the velocity is in meters per minute and the time is also in minutes. So the first thing I want you to do is to figure out if you were to calculate the distance the bottle traveled using 3 sub-intervals, what is your delta x? So going from 0 to 60, and I only wanted to use 3 sub-intervals. So this is very similar to trapezoids. How do you figure out the width of those trapezoids? This is the same thing. How do you figure out the width of your rectangles? For B, calculate how far the bottle travels during that hour using a left, middle, and right Riemann sums with 6 subintervals. Then calculate a left and a right using 12, and then calculate a middle using a middle Riemann sum also using 12 subintervals. So go ahead and pause the video, see if you guys can come up with this, and then come back and take a look at the answers. So for A, to figure out your delta x, what you do when you're given a table of values or even when you're given the graph, you do your B minus A, so 60 minus 0, and you divide it by how many subintervals you want. So 60 minus 0 over 3, I want 3 subintervals. That means my delta x, my width of each rectangle, is going to be 20. And so that's just figuring out the width. I didn't tell you to use a left, middle, or a right, so we're not actually going to determine this right now, but just calculating the delta x. For B, it said to use a left, middle, and a right Riemann sum with 6 subintervals, so I needed to change my delta x, so I did 60 minus 0 over 6, and that means my delta x is going to be 10. And since I'm using the left side, so if my width is from 0 to 10, my left side is going to be at 1. And then from 10 to 20, my left side is going to be at 1.7. From 20 to 30, it's at 1.8, etc., until you get to 50 and use 1.5. When we get to the middle, my width doesn't change, it's still 10, but now going from 0 to 10, my midpoint is at 5, so I want to use the y value at 5. From 10 to 20, the midpoint is at 15, so I use the y value at 15, etc. And then you add those and multiply them by 10. And then the last one, my right Riemann sum, width is still 10, but now from 0 to 10, my right side is 10, so I'm going to use the y value at 10 to be 1.7. From 10 to 20, the 20 is the right, so use the 1.8 until you get to 60, where the y value at 60 is 0. So notice with this one, the left is 84, the middle is 90, and the right is 74. It didn't go, it wasn't just constantly increasing from a left, a middle, and a right. And that's because if you look at the values of the velocity, it increases and decreases over time. And so you can't always guarantee that the left is the smallest and the right is the biggest. It all depends on the function or the table. For C, it said to calculate how far the bottle traveled using a left and a right with 12 subintervals. So I needed to change my delta x from 60 minus 0 over 12. I get a width of 5. And so going for 12 subintervals, since my width is 5, so my one rectangle is from 0 to 5, using a left I would use 1. From 5 to 10, my left, my y value would be 1.2, etc., just until you get to 1.2. And then if it was a right, my width is still 5, but now you use the values on the right side. So from 0 to 5, I'd use 1.2, from 5 to 10, 1.7, all the way till you get to 0, and you get 82. And the last question I asked you to use was to calculate a midpoint Riemann sum with 12 subintervals. But with my width being 5, 0 to 5, I can't do a middle Riemann sum or a midpoint Riemann sum because I don't have the values at 2.5. I don't have the value at 7.5. And so I wouldn't be able to calculate this because you don't have what occurs in between 0 and 5 and 10. So you want to make sure you have the right information and you have enough information to answer the question. So a couple little bits about notation. So notation using a Riemann sum to approximate a definite integral. So you're going to come across a couple of problems that look like this. This is the notation for a definite integral, but we are not going to learn how to evaluate this quite yet. That's the fundamental theorem of calculus. So right now we're going to use Riemann sums. And so what we do is we take our limits of integration, so we're going from 1 to 4, and I want to use 6 subintervals. So I do 4 minus 1 is 3 over 6, and I get a width of 1/2 or 0.5. And then to find a left, a middle, or a right, my lefts are going to be, and I'm not giving you the values for this, I'm just showing you how to do it. So my width, once again, it's the same. It's always going to be 0.5. And so since I'm going from using my left side, I'm going to have f of 1 plus f of 1.5 plus f of 2, whatever those values are when you plug them into the equation x squared until you get to 3.5. Notice that the x values that I use are the same width as my delta x. For a midpoint, I would use, so between 1 and 1.5, my midpoint or my middle Riemann sum would be at 1.25, 1.75, 2.25, etc. And for a right Riemann sum, I'm going to start at 1.5 and go all the way to 4. And then those would be my, I would calculate what those values are to get the approximate area. So try one on your own. I want you to approximate the area using a left, middle, or a right Riemann sum with 3 subintervals. So go ahead and pause the video and you can come back and check out your answers. So what you should have figured out first is your delta x. So when you're going from 11 to 5, or 5 to 11, and you want to use 3 subintervals, 11 minus 5 is 6, 6 divided by 3 is 2, and so then your 2, sorry, this should have been a 2 out here. My 2 is out front because it's the same width, and then I used the y values at 5, 7, and 9, and that got me 160. My midpoint Riemann sum from 5 to 11, my midpoint occurs at 6, 8, and 10, and so I got 180. And then my right Riemann sum, I used the y values at 7, 9, and 11, and I got 204. So just to take a look at what that looks like, you had the graph of 4x minus 2, and we are trying to figure out the area under the curve from 5 to 11. And so here is an example of my left Riemann sum, just going from here to here. It's an underestimate. This is just because it's an increasing function. I haven't done any examples with decreasing. Here's my midpoint Riemann sum and my right Riemann sum, and what those look like just even with a linear function. So then just very last thing, you might see a couple things called an upper and a lower Riemann sum. Upper and lower depends on what you're going to use, like a right or a left. Completely depends on if you have an increasing or a decreasing function. So with an increasing function, your upper Riemann sum, you're going to be using the right y values because those are the larger y values. With a lower Riemann sum, you're going to use the left. With a decreasing function, your upper Riemann sum, you're going to be using the left Riemann sum because you have higher y values for the left. And for a lower Riemann sum, you're going to be using the right Riemann sum because you have smaller y values over there. And your assignment, page 209, numbers 1, 3, 5, 9, 10, and 11. Have yourself a great day.